All right, so we're back. Welcome to Wednesday, the 12th. We are going to finish up a couple things on hashing, and then we're going to go into another topic, which is actually a topic that could take an entire semester if you wanted it to. I've seen whole classes talking about this, the next topic, but we will touch on some various things. It's called graphs, which is an interesting topic in computer science, but one that we will kind of go that deep into a giant ocean of material. Okay. Questions before we get going? Any questions on the homework? Homework 4 due Friday. Remember, I will be very reluctant to give any extensions. You've had not too much, but you've had plenty of time to work on this assignment. So yeah, question?
So to clarify, we're going to be submitting 9 files, right? 3 main.
You'll be submitting at least 9 files, plus a make file, plus a README, plus any other files that you might have needed to write, like a queue or something like that. Yeah. Yep. And if you have trouble changing the make file, let me know. It's not hard. Just read through it and go, oh, I see what's going on. Or look up make file. But if you have trouble, let me know. We'll figure it out. Yeah, Ben. Different Ben. Yeah.
For some sorts, it's hard to do with negative numbers.
Right.
Will you be testing negative numbers? Because I know Dijkstra is.
Yeah, Dijkstra, you're not going to be able to do negative numbers very easily. I mean, you could just say, look, if it's negative, you're just going to do another pass at the end and move all the negatives behind the positives, right? That would be easy to do. But no, I don't think we will not be testing on negative numbers. But you got to go from 0 all the way up to maximum, whatever the max int is. Okay. Any other questions, Retta?
So in the review, when we talk about the files included, all of the list files aren't actually things we need to talk about, right? Like when you give the random list of integers.
No, you don't need to talk about the random. You can just say, no, you won't be. Those won't be being provided. You won't be providing the random lists. No. Yeah, Dave.
For the tests, how big should we be expecting the?
At least 100,000 integers. Okay. Yeah, at least 100,000.
More than a million or less?
At least 100,000. That's all I'm going to tell you. If you need to do more than, or if you want, you can test on more than 100,000, but I won't be testing on more than 100,000. Yep. Okay. So at least 100,000, probably not more than 100. Well, not more than 100,000 then. I'll leave it at that. Make it 100,000. Any other questions? Okay. All right. So let's go back to what, just remember for a second this cryptographic hashing we were talking about the other day. Okay, cryptographic hashing is taking some string, it can be any number of characters long, and creating a hash, which is also a pretty long string. I mean, maybe 100 or 200 characters long, right? And then, and those hashes are hard to find out what the hash, what created the hash. That's kind of the really important part. It's hard to find another string that also can hash to the same value, right? It should be fast to hash the values. And then what was the fourth one? There was a fourth one in there too. Hard to find out what hash or a hash that matched it to it. What was that? Yeah, that was the fourth one. If you change a hash a little, if you change a string a little bit, it should create a completely different hash function. All right, good. Okay, so we talked about a number of different examples. There's at least one that we missed here. Sometimes you can have what you call a digital signature on a file or an email, right? And I do this in the Navy all the time. We have a little certificate and we send an email, and I know that it came from the person that it says it came from, unless that person's little ID card got stolen, which probably doesn't happen, right? And somebody would have to steal the ID card and know a password on top of that. But how do you actually do this? Well, it's this really cool type of encryption called public-private key encryption. Nobody even knew what this, nobody had even discovered this until the 1970s, I want to say, maybe 1980s. And it actually allows you to pass information back securely without ever meeting in person. And this is a huge big deal because the way most encryption schemes work, you have a key that you say, hey, use this key to decrypt something, right? And you guys have to, and spies used to have to meet up in the middle of the night and exchange keys, right? Or when submarines used to go out, they would have to, they still do actually, but when submarines would go out, they would take like a code book that would have all the different keys in them, and you'd have to make copies of these keys, and it was just generally inconvenient to have encryption happen. What happened when people created this public-private key encryption scheme was they made it so that you can get encryption between two people or computers or whatever without ever having those people meet in the middle, like meet somewhere and say exchange things. So it makes it so that Amazon.com, eBay, all those places where all your credit card transactions, all those things happen such that you can be assured, more or less, that they're secure, and you never have to actually go and like exchange these keys. So it's pretty cool stuff. Here's how it actually works. Okay, Alice has two keys. Okay, one's called the private key, which only she can know, or it's on her computer or whatever. And she also has a public key, which is created from the private key, and she can give that out to everybody. Okay, she can go, here's my public key, and give it to somebody. Okay, and what she can do is she can take a message that she wants to send to Bob, and she can encrypt it using her private key. Okay, and what that means is she runs it through this algorithm, and it takes and it turns it into some hash values, and those values can only be decrypted with her public key. Okay, so what she does is she creates her message with her private key, sends it to Bob. Bob goes and finds her public key, applies it to the message, and it comes back out as the message. And he says, I am guaranteed that only Alice created that message because she's the only one who had her private key. And the only thing that could have created this encrypted message is Alice's private key. Okay, so it's a guaranteed way of saying, oh, great, that definitely comes from Alice. And you might be able to think of various situations where you might want to make sure that an email came from somebody in particular, right? So you might want to make sure. OK, Aaron, and then
so in
Maggie.
this case, you actually, with the public key is actually an algorithm for getting the message back from the hash.
Yes.
But that's OK, because if we don't know how the hash was created in the first place, then it's unique to Alice, and we know
Yeah. Yeah, be careful. It's not. We do know the algorithm. We just don't know the pieces. It's like two puzzle pieces that have to be working together to actually decrypt the message. So.
But the point isn't to keep people from reading the message.
Right. No. Right. In this case.
Everyone has.
Right. Everyone has public. Right. This is not to keep people from reading the message. This is to make sure that it came from Alice, which is a very distinct difference. Many times you will do both. You will actually encrypt it and sign it, and you'll know that number one, it came from that person, and number two, only you will be able to decrypt it. So that'll be interesting. Maggie.
My question was essentially, like, how are you allowed to unhash it?
Oh yeah, you unhash it by using the public key that's available to everybody.
So like in normal encryption, we want that to not.
Oh yeah, that's the exact opposite. So in normal encryption, it's the exact opposite. Here's what happens, and this is actually the coolest thing when you think about it. Alice, let's say Alice wants to send an encrypted message to Bob, one that only Bob can decrypt. What she does is she encrypts the message using Bob's public key, and she turns it into a message that only Bob can decrypt with his private key. So it's exactly the opposite. Right? So it actually, the math is like identical. It just works the exact opposite. If you apply the private key, if you apply the public key to a plain message, it becomes encrypted. And the only thing that can decrypt it is the private key. If you apply the private key to a message, then the public key can decrypt it. So it's exactly the opposite. And both of those cases allow for signatures and security.
But like with passwords, for example, when we were talking about that,
Mm-hmm.
those were different.
Yeah, passwords don't use this. There's no way to go backwards.
Yeah,
Right. There's no way to go backwards on a password. Hopefully, that's kind of the idea. Yeah. Charlie had something, and then no. Okay. Go ahead and then yeah.
So when you were saying like companies like Amazon or something would use this, that you knew you were actually giving your information to Amazon.
Yeah.
How would you know if like what would it like? Would your screen like? How would you know that it didn't match up?
How would you know that? Well, what do you mean? How would you know that it didn't match up?
What is their signature? For, like,
Yeah,
how
like
do
I
you
never
their
see like
signature?
it's like, oh, this is Amazon.
Well, actually, if you ever go to a website that's a secure website, you can click on it and you can actually see the signature. If you want to, you can see it. At the risk of taking a little extra time. Oh, by the way, have anybody actually written a scientific paper yet? A couple people have written some scientific papers. If you ever write a scientific paper, make sure you proofread it, because what you don't want to happen is for the following to get into the journal, which did happen. See, can you read that? No, you can't read it. Right? You don't want that to get into the journal, which is actually what happened in this real-life example. OK, so look, I happen to be on Twitter right now, and see the little lockup here? If you click on this, you can see the certificate, and you see how it's got all these like signing things here? You can get down, it's not going to show it here, but you can get down and you can actually, there, signature algorithm. Well, that tells you how it's done, and then the serial number, and then let's see. I think you can actually, if you dig far enough, you can actually get down and get the actual key. That might be it right there.
Now, how
So-
do you know if that wasn't true?
How do you know that? Well, that's a good point. So if you read through this, that's a very good point. How do you know that it's like actually the right one? Yeah. So you go and you go, OK, this was signed by Symantec, right? And Symantec is known by your web browser as being OK. And so if somebody would have to break, and then that was signed by Verizon, or VeriSign, which is also known by your browser. It actually ships with the browsers themselves. So lots of cool ideas. I don't want to take too much time on this, but lots of cool ideas on how this stuff works. OK? So bottom line, you can both sign an email and encrypt it using this very cool public and private key cryptography. OK? So it's pretty neat how it actually works out. OK? And Alice is the only, or Alice is the only one. If Bob hashes a message with Alice's private key, that's wrong. It should say, if Bob hashes a message with Alice's public key, only Alice can read the message by decrypting with her private key. That's actually incorrect. Change it right now. Public. There you go. OK, so questions on that? I mean, I'm not going to go into lots of details, but it's kind of cool. Yeah, Kenny, and then.
Oh, how is it different if Bob hashes a message with Alice's public key and if Alice does it with her public key? Doesn't that mean that anyone can?
Yes. Well, OK, so Alice isn't going to hash anything with her own public key because she's the one making it. She will take either her private key and hash something. And then anybody with the public key, which is available to you or you or you, can decrypt it. So that's to sign it, to make sure it absolutely came from Alice. The flip side is if she takes her, if someone else takes her public key and encrypts a message, then she can decrypt it with her private key.
Okay.
Yeah. So if I want to send you a private message, only you can decrypt. I have to know your public key. That's how it works. And I encrypt my message with your public key, and you're the only one who can decrypt it. Yeah. Yeah.
So what kind of a function has this two-way behavior, but no way to
Yeah.
how to go there?
Go look it up. I'm gonna go look up public key cryptography. You will find a zillion things online about how the actual algorithm works. It involves big prime numbers. It involves raising numbers to a big power. It involves modding numbers, et cetera, et cetera. But it is really neat, and it was cool when it was invented. Yeah, still pretty cool. Question, Charlie, and then yeah. OK. Yes.
I have a question
Jan.
on how the public keys communicate. How will you know that this is a specific public key that should?
Right. You can send a public key to someone. You can email a public key to someone. You can give it to them on a flash drive if you wanted to. You can have it stored in a repository that you know is secure. That's how it works.
So if I have Alice's email and Bob's email, so it will first identify like this is Bob and then go find it.
Go find his public key. Yep. Yep, that's exactly right. For the Navy, what happens is there's a big global address book that has all of our public keys in it. So if I want to send somebody else in the Navy a private message, the address book looks up that person's private key, or sorry, public key, and I encrypt and then encrypts the message with that. So yeah, good question. Yeah.
So, in a way, it's sort of so the public key and the private key.
Yeah.
The thing is, they have to mesh, and so there
They
has
do.
to be a way. There has to be, like the whole point of it is that you can like encrypt and then decrypt.
Yes.
So, how is it easy to find two algorithms that are inverse? But it's
Look
not
it up.
easy
Right. All I'm going to say is,
Make, but not each
I know it's really like it's complicated, but it's actually pretty cool. Look it up, and you'll see how it works. No, I'm just saying we don't have time to go into it, and I don't know all the details, but it's neat how it works. So look up public key cryptography. It's right on the Wikipedia page, and it goes through all the math you need to do it. Yeah, Alex.
Is this what PGP does?
PGP is exactly that. Yep, pretty good privacy. I think it's called. It's a public-private key system. As far as I know, it is. Pretty sure it is. Yeah. Okay, so that's that. That's mostly what I wanted to talk about for hashing. Okay, lots of cool stuff on cryptographic hashing. Let's see. Not next semester, but the following semester, there will be a cryptography class taught here at Tufts. They only teach it like once every 4 years or so. So if you feel up to the challenge, if your math skills are pretty good, you might want to try taking it. You probably should have Comp 170 beforehand, which is a little tough to do as like freshmen, sophomores, juniors. But if you want to take it, talk to me, and then I'll put you in touch with the professor, and he can tell you what the prereqs are. Okay? All right, any other questions on hashing or that sort of thing? Okay, so let's move on. This next topic, called graphs, is you may think you've heard of graphs before, but that's probably not what we're going to talk about today. It's going to a slightly different idea. Graphs are a giant topic in computer science. Okay, it's a huge topic, and it's used all the time. And these graphing algorithms are used for a ton of things. Had anybody ever used a GPS to like find your how to drive from here to Trader Joe's or whatever, right? Right? Uses graphs in the background to do this. And so it's a huge topic. We're going to just touch the surface of it, but hopefully you'll find it kind of interesting. Okay? All right. I'm not going to do any like Unix tip of the day. At the end, I'll show you this graph, and maybe in the middle, I'll show you this software you can use to model some of these graphs. I'm still trying to figure out why it's not doing one or two things that I'd like it to, but I just found it like yesterday, so I guess I can't complain. We are going to talk about graphs in computer science sense, and graphs look like the picture on the left here, okay, which is just a bunch of what you might call nodes, although we call them vertexes instead of nodes in graphing language. And they have little like pointers to other vertexes or vertices. Okay, that's a graph. We're not talking about this, right? We're not talking about like a graph of a data or whatever. We're talking about a specific type of linking between vertexes in some object. Okay. You might start to think, okay, well, this is going to be a little bit like trees or tries or heaps or whatever, right? Kind of true, but this is like the Wild West versus trees, right? There's no structure to a graph necessarily. Okay, trees have very defined structures. Graphs, no structure. So that's why it kind of comes later in the semester, because it's a little more unstructured, and it's a kind of a bigger idea trying to process these things. Okay. So what is a graph? It is, like I said, it's similar to a tree, but it's just nonlinear. Like there's no, and not even structural really. The structure is like not present. The Wild West, I like to call it. Okay. Here's a very simple graph. Okay. All it is a bunch of vertices and edges. Vertices being the, in this case, the circles. You might call them nodes. Okay. And by the way, the computer represents this very differently than a lot of the other things. We will get into that. Normally, it's like a table or something. We'll talk about that in a few slides. Okay? You've got these vertices, and you've got these edges connecting the vertices like this. Okay? This is called undirected. What's the difference between this graph and the previous one, besides the numbers? Arrows, right? What it means is there's no defined direction between these two vertices here. Right? There's no defined direction. It means that if these two are connected, you can connect them, and they're just connected. Like there's no like direction one way or the other. Versus the arrows, which means it's directed. Okay. We call the edges. We generally label them with E. We normally label the vertices with V. It depends on what you're doing. A lot of times, just number them or label them with letters or whatever. It doesn't really matter. This is basically just a label on it. Okay. A lot of times, the edge will be what we call the weight of the edge. We'll get into what that means. You'll actually have a little number there which talks about how much that edge is weighted, which we'll get to in a few minutes. Okay? All right. The structure of a graph, like the picture of a graph, if you're thinking of this visually, it doesn't matter what the picture is as long as all the edges and vertices are the same in the same structure. Then this graph on the left here is the exact same as the one on the right, meaning that it doesn't matter if v0 and, let's see, v4 is way down here in this one and way up here in the other one, right? Visually, this is one problem where graphs are very visual in a lot of ways, but sometimes if you can't figure out a graph, go look at the actual underlying structure, which formalizes it a lot more. But those are exactly the same, unless I screwed something up. But hopefully I didn't. Right? If you look at v0, v0 connects to v1 and connects to v4, and v0 connects to v1 and v4, etc. Okay? Like the structure of the lines does not matter for this type of scenario. Okay? Questions on that? And the length of the line doesn't matter. We may label them with amounts, but like the drawing part, not important, just helps out to understand what's going on. Okay? Can you think of a social program that might use graphs all the time? Facebook, right? This is like you and all your friends, right? You're connected to so-and-so and so-and-so, and that's connected there, and that's connected there. And I mean, it's pretty cool how that's, they use those types of things. You've got to be an expert in graphs if you're going to work at Facebook. Yeah?
Yeah, Twitter's API actually just gives you like tons of just matrices and graphs. Just like
Twitter's API does the same sort of thing? Yeah, they just give you, there's lots of like kind of group dynamics that can be modeled with this sort of data structure. Okay? Well, Wikipedia is probably based on, it's a database sort of thing, but yeah, I can see what you mean. It's got lots of different edges connecting various articles, sure. Yeah. Okay, I want to show you a little graph example here, okay, using the coin game. Okay, you'll see coins on the screen here. We've got a head and a tail and a head. Okay, and what we're going to do is we're going to have just a little game. It's not a particularly hard game. Okay, anybody? I saw somebody the other day playing like Super Tic-Tac-Toe or whatever. Have you guys heard of that one? It's like the latest thing. It's like tic-tac-toe. It's like this. It's like you've got. It's kind of like it's like tic-tac-toe, except each one of these things has a little tic-tac-toe board in it. Have you seen that? And what happens is if someone goes here, then the next person gets to go down in this one and has to go somewhere down here. And if this person goes here, or the person goes there, then the next person has to go up here. And it's like an extra level of complication, which is necessary with tic-tac-toe because it's tic-tac-toe and it's not exactly hard, right? But that, I guess, gets a lot more intense. Anyway, okay, heads, tails, heads for this game. Now here's how the game is played. You try to go from heads, tails, heads to tails, heads, tails by flipping various coins. Okay, by flipping various coins. And you try to do it in the least number of moves or whatever. Again, this is not rocket science, but it's a kind of a fun little game. Okay, the rules are as follows. You can flip the middle coin anytime you want. Okay, that's allowed. You can only flip an end coin if the other two coins are the same. Okay, so the only time you can flip an end one is if the other two are the same. They can be the same as the end one or different, but the other two have to be the same coin or the same side. Okay? We can actually do this with a graph. Okay, we can actually set up a graph to help solve this, or to at least define the whole problem. Okay? And it turns out there's actually 8, let's see, is the next one? Yep, the next one's there. Anyone want to walk me through like a solution to this? I'll write this down. We go heads, tails, heads, and we're trying to get to tails, heads, tails. Somebody give me a first move that I can do. Somebody from over here. Yeah, go ahead. Go ahead. Whoever. Flip the middle. So I'm allowed to flip the middle. Is it the only thing I can do? Yeah, it's actually the only thing I can do because the two on the end are the I can't flip this one because these two are different, and I can't flip this one because those two are different. Okay. Whoops. Sorry, I'll do this one. Okay. Now what? I could flip the middle again. That would be a little silly. But I could do it. Okay. Let's flip one of the sides. Which one? Left. Okay. Okay, now what? What's that? The middle of the tails. Yeah, you can only flip this one again, right? So middle's got to go to tails. Then what? Then we can now go do this one to tails. and then we flip the middle one, and now it's tails, heads, tails, and we've won the game. Woohoo! Right? OK. We can make a graph out of this by just kind of enumerating all of the different states that are possible here. OK, we can enumerate this. There's 8 different states, as it turns out. And how do we know there's 8 different states? 2 to the third, right? Because each one of these states has 2. If you take any kind of combinatorics, right? There's 2 states for this one, 2 states for this one, 2 states for this one. Altogether, there's 8 total states, right? And here's the graph. All right, it looks a little like this. And it doesn't quite look like the nodes we saw before, but you can tell here's the heads, tails, heads, and we're trying to get down to tails, heads, tails, right? And the possible solutions go from this one to this one, which we all did. We actually went to this one, I believe, and then down to this one, and then to this one, and then to this one. You could have gone the other way, right? You could also go around and around, right, and around, and then that way if you wanted to. You could keep going all day, right? But the minimal solution is this one right here. 1, 2, 3, 4, 5. And you can always go between the different states. It's not a directed graph because you can always go back to the state you just came from, no matter what state you're in, because of the way the rules work. OK? All right. So you see how that's a graph? OK, a lot of times we will model, you can model various games like this. I mean, I suppose you could come up with a tic-tac-toe game that's a graph and then kind of figure your way around the graph. It'd be kind of a fun problem, actually. But you could do that. OK? All right. So that's undirected graphs. Now let's talk about directed graphs. OK? The directed graphs are actually somewhat more interesting in some sense because you all of a sudden have to go in one direction. You can't go the other way necessarily. OK? So this graph up here, it has from this vertex to this one, you can only go that way. You can only go this way from this one. You can go this way, but then you can go back to this one if you wanted to. Or you could go up to this one and then around back to the first one, et cetera. Are there any that you can't get to if you start from another ones? Yeah, this one, right? You can't get to that one because no edges actually go inbound to that one. Okay, you have to start with that one if you're going to get to any of the, if you want that one to be included in your final answer. Okay, or in your final traversal. This. Okay. All right. You can also get a little crazy with this, right? You can have graphs that have a loop to it, like you can have a graph connects to itself, right? You don't see this. Well, you actually do see this somewhat often, but you hopefully wouldn't see this on like Google Maps or whatever, right? Where I want to go from Boston to Boston. You know, I mean, you're not going to see that really, right? You're generally also not going to see the case where you have multiple edges like from one to the other. That doesn't seem to make, you don't see that too often. I mean, why have both when you can have one? Although maybe in Google Maps, this might be 2 different roads, right? Maybe this is the highway and this one's the regular local road, and you want to, one's got a different weight or whatever. So you can see that. But that's how, those are some of the other kind of interesting parts of graphs. Okay? How do we actually represent graphs in our code? So one way to do it, in fact, some would say the best way to do it is using this thing called an adjacency matrix. Okay, here's how it works. I've tried to create this from this graph here, the 1, 2, 3, 4, 5, 6, 7, and all these different connected paths. Okay, and what it says is like the rows here are the same as the columns because you can actually go from any to any other one in this case. Okay, so if you want, so in this case, node 1 goes to vertex 1 goes to vertex 2 and 3 and 4. So vertex 1 goes to 2, 3, and 4, and we just say it's true in there. Okay? Or you could say it's 1 for like the weight of 1, which we'll get to in a few minutes. Okay? So that's how one way to represent it. This tends to take up a lot of space, right? How much space? N squared amount of space, right? If you have 1,000 nodes, you're going to need a million. You're going to need a million entries in your matrix, right? Because 1,000 by 1,000. So it's kind of a lot. And by the way, most of the time, you're not going to fill up much of this, right? We can actually say we have a complete tree. Complete graph. If we have edges connecting everybody else, that is somewhat rare, right? I mean, just to draw it for a few, right? if we have 4 here and we try to connect everybody to everybody else, right? Let's see. That guy, and did I do it with those ones? That's now it. But if I add another one, right, this is got to go there and there and there and there. And if I had edges on there, it's kind of exponential in the growth for these things, right? So it's not normally that you have these connected like this in this kind of graph. Yeah. Oh, you could also have the self ones. Yeah. In this case, even this wouldn't even fill up the whole thing with trues, right? Because which ones would be not filled with this one? Diagonals, right? Down there, they would still also be false. So if you wanted, you could then have like this and this and this and this and this, and then that's finally like a complete tree in terms of the matrix. So, but you rarely see that. Yeah.
Like, and then on top of that, you might have multiple. Well, how would you represent multiple edges to the same node?
Right. Multiple edges to the same node is hard. Yeah. With this one, it's hard. Now, by the way, with an undirected graph, this is also the undirected graph here, right? So every time you have a 1 to 2, you've also got a 2 to 1 for this one, right? Up here, you would need to actually put arrows on all these to make them, if they're directed, and then everybody would have another one, right? And you'd have to double up on everybody. So yeah, so it's kind of intense when it comes to directed graphs and filling up this whole adjacency matrix. So most of the time we don't use an adjacency matrix. Sometimes we do. It's actually easier to, it's a little easier to read in some cases. Some might say it's harder to read, but it's definitely provides constant lookup, right? If you want to know if there's an edge between 4 and 6, you go 4 and 6, and boom, you're right there, right? Where 4 and 6, right? Or 6 and 4, there isn't one, for instance, in the directed graph. Okay, so it's nice in terms of speed, not so nice in terms of space. Instead, Instead, what we can do is we can do what we call an adjacency list. Now, this same graph gets compressed down to this nice little list here, right? Which is on the order of the number of edges plus the number of vertices. And what's going on here? 1 goes to 2, 3, and 4. And we see that right up here. 1 goes to 2, 3, and 4, right? Directed. 2 goes to 4 and 5. 2 goes to 4 and 5, etc. 6 doesn't actually go out to anybody, so it's empty. So you see how this compresses that down pretty nicely? Problem with this is, what if you want to know, does 1 go to 4? What do you have to do? You have to do like a search, right? If this is whatever list this is, you have to go 1, 2, 3, 4, and you have to actually search it. So it's a little bit more time in that sense. If you want to figure out if 1 goes to 4, how do you do that? On this one, you go 1, and then you go, OK, is that 4? No. Is that 4? No. Is that 4? Yes. So you have to search this one. Versus the other one, where you can go right to the right place in the matrix. So it's slower, but much more compressed in general. Yeah?
So I guess I'm not, so I'm looking at the ON, and I'm seeing, I'm thinking it's not about the number of vertices, it's about the average number of connections per vertex.
OK, so
it's like,
worst case is order n. Worst case is order n.
because then every vertex is connected to every other
Yeah.
vertex.
Well, or, right. I mean, yeah, right. If everyone's connected to everyone else, it would be that for the worst case. OK. Any other questions on this one? Just a couple different ways of showing it. Many times we'll do it this way just because it's easier to see, and we'll do it with this adjacency list. If you want a little more like ability to kind of see the whole thing, you'll do it in a matrix. Okay? All right. And in this case, you can actually store these using a hash table, right? You can actually say the keys are the vertices and the lists themselves are all the edges. Pretty easy to do. Okay? Or the edges are lists. Now we get into the more interesting part of graphs, when we talk about this idea of a weighted graph, okay, and weighted paths. So now I've got tons more numbers on here, right? In this case, what this means is vertex 1 has a weight of 1 to get to vertex 4, and a weight of 2 to get to vertex 2, and a weight of 4 to get to vertex 3, etc. Okay? And when we say the weight, well, a lot of times we'll be adding up the costs of these things. If you're thinking about a map, like Google Maps or whatever, right? You might want to you might think about like 1 being like the highway, or maybe 1 being a close by city, right? So if you're trying to go from Boston to Providence, Rhode Island, which is right down the road, it might have a weight of 1. But if you're trying to go to New York City, which is much farther, you're going to have a weight of 2, right? And if you're trying to go from New York City to, I don't know, Miami, you're going to have a weight of 10. You see how that works? It's all about the whatever you're weighting on. In that case, it would be the distance, let's say, or the time it takes to get to a particular place. Okay? And so when we say what is the cost to traverse an edge, that's just the number. When we talk about the path length, that's adding up all the different individual edge costs or weights as you go along. So if we want to go from 1 to 6, one way to do it is to go to V1 to V3 with a weight of 4, and V3 to V6 with a weight of 5, and that would have a path length of 9. Okay, there's other path lengths too, right? You've got a path length of 1, well that's also happens to be 9. You could also go 1 and 2 is 3 and 5 is 8, so that's a different path length. You see how that works? You've got different path lengths now. And this is where this stuff gets kind of interesting. When you start thinking about, oh, what can we do to figure out what the best lengths are and so forth. Okay, so it starts to get really cool. Okay. All right. So here's what we're going to do. We're going to start talking about some shortest path algorithms. Okay, this is like the bread and butter of graphs. If you remember anything from graphs your entire rest of your life, remember the algorithms we're going to talk about today. Okay, you'll have to know them for the final two, right? This is kind of a similar, like this picture shows, the like plane routes, right? And if you're flying to, let's say you're flying to San Diego, one way might be able to go straight there, one way might be able to go through Houston, etc., from Boston, or so forth, right? And the idea is try to find the shortest path from one location to the next, from one vertex to the next. Yeah.
Wouldn't the most direct route always be the shortest?
Wouldn't the most direct route always be the shortest? For flying, probably. For driving, not necessarily. Right? I mean, if you ever have to go through a big city, sometimes you're like, I got to go around it. Right? Even though it's more distance, you're going to take less time. It depends what you're looking for, right? If you're trying to save gas money because you don't want to drive as many miles, well, maybe. But then again, you could be sitting in traffic. So it depends. Right? Depends on that. So this is really like I said, the bread and butter of graphs. Okay? Oh, we already did this one, didn't we? Shouldn't have picked this one. What's the shortest path from V1 to V6? Who says 6? How do you get to 6? Starting at V1, where do you go next? V4 for a path length of 1, and then V7 for a path length of 4. So that's a total of 5, and then to 6 for a total of 6. Yeah. So actually, we didn't do that one. We got close, right? But it's not necessarily the one you'd first think about, right? You might think, oh, I want to go 1 to 4 to 6, and that'll do it. But no, we had to go we had to go around a bit because of the different weights. Okay. Now the question is, how do you figure that out? That's how do you figure that out without going this one and this one? Some of you guys might have just done what we call what do we call it? Not a comprehensive search. I don't know why I'm blanking on it. No, there's depth first and breadth first, but I don't know why I'm blanking on the word. Where you try all the cases. All right, that's kind of what it sounds like some of you guys were doing. You're like, well, I'll try this one first, then I'll try this one, then I'll try this one. Did anybody try to go around this way? Right, and you get to this one, you're like, oh, no, forget it. Right? Yeah, greedy's not, we will get to greedy algorithms, but I'm trying to think of I forget. I'll think of it. I'm sure I'll think of it in a second.
Like the maze.
Yeah, well, the maze that we did was an example of this sort of searching, and we'll talk about that again in a little bit. Okay. All right. So we know it was V1 to V4 to V6. The shortest unweighted path was 2 because you just go V1 to 4 to 6, and you forget about the weights, and everybody just kind of becomes a weight of 1, and you say, what's the path? 1, 2 to get there. So that's the unweighted path. Okay, and they don't always have to be the same, of course. Okay, and notice there's actually no path backwards. You can't go from v6 to v1 because you can't go from v6 to anybody in this case. Okay. All right. Turns out you can actually make negative weights as well. Negative weights get a little bit weird because let's take this. Some of the numbers are definitely different on this, right? And I actually changed some of the arrows to make this work out as well. But in this case, so v5 to v4. So let's look at v5 to v4. That has a weight of 1, right? But if you go 5 to 4 to 2 to 5 and back to 4 again, 5 to 4 is 1. 4 to 2 is 3, so that's a total of 4. 2 to 5 is actually now it's negative 6. 5 to 4 gives you negative, did I do this? Yeah, negative 5, right? If you kept going around, you'd get negative 11. It actually gets shorter and shorter and shorter if you're talking about like actual like shortness, right? So these are called cyclical graphs, and there's no defined shortest path. Right? No defined shortest path. Yeah?
So in the same way that you can restructure your graph such that all of the edges and the vertices, the connections between the vertices are conserved, can you do, if you have negative weights, can you change all of can you add the smallest weight such that everything becomes positive? Does that conserve traits about the graph?
Would that actually make sense? Well, you might not find the shortest in that case. Like, it turns out if you just added 10 to everybody, or 11 to everybody, or whatever, yeah, that would actually work, but sometimes it doesn't work for the way you think it would. Yeah, you can't actually say, okay, fine, make everybody positive and then do it. We'll talk about that, probably not today, but maybe tomorrow, or Monday. Yeah, good question, though. Good question. Okay, any questions on this one, though? You can't, if you have negative graphs, you're going to have to go, whoa, wait a minute. I got to think about this a little bit more, and we'll figure that out next week.
That's how Superman turned back time.
Yeah, that's how it's right. Exactly. Okay. So here's what we're going to do, and we're going to walk through a couple of examples here, and we're going to walk through the example that for the unweighted graph first to try to figure out if we can make this into like a little bit of an algorithm, right? Because the idea is you don't want to do that exhaustive search where you're doing all the different choices, right? That would be crazy if you had to do that. Okay. So let's say we're going to find a path from one vertex S. We're going to pick a vertex to start with. So what we're trying to do right now is, in this case, we're going to pick vertex 3. And we're going to say, what's the shortest path to everybody? Okay, not just 6 in this case, but shortest path to everybody. Okay. What we do is we pick v3, and then we say, fine, what's the shortest path from 3 to 3? 0, right? There is no other path. Right? I mean, you're not going to get better than 0. Even if you went circularly around, you're not going to get better than 0. Okay. No. From vertex 3 to vertex 3, there's no looping, and there's no you can just be, you're already there. You don't need to go anywhere. It's like being at home and telling your GPS, take me home. You're already there. Right? So it's 0. All right. That's what we're talking about here. Yeah, you don't have to go all the way around. Okay? All right. And then what we do is we say, OK, we've marked that path for 0. Okay? And then what do you think the next ones we're going to look at are? The ones that come from 3, right? So you're going to then look at 1 and 6. And it doesn't matter which order you look at them in. All right? And what's the path length going to be to 1? 1, because you're 1 away from it. Path length to 6 is also going to be 1. Okay? All right? And that's what you do there. OK, what's the next ones we look at? Well, why 2 and 4? Because the 1 goes down, that's fine. I mean, you could look at anything that 6 goes to, but it turns out it doesn't. Right? So yeah, in this case, we'd look at the 2 and the 4. How far is it going to be to 2 from 3? Add another 1. And then here add another 1. So it's going to be 2 to those ones. Okay. All right, there we go. So we've got the 2 there. Okay. Again, no paths from v6 to anybody else, so you don't bother looking. I mean, you look, but you see, hey, there's no paths from 6 to anybody. Okay, the next ones we look at, of course, are 5 and 7, right? I mean, I guess first we actually look at, we pick maybe V, we take either one of these, and we say, okay, we haven't looked at 2 yet, so we're going to look from 2, goes to 5, and it goes to 4. So the path to 5 is going to be how much? 3. How about to 4? Still 2. You don't change the ones that are already less, because you're trying to find the shortest one. It would be 3 if you went bing, 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 right? But you can also go just there. So you don't need to worry about that. That's nice. Okay. And now we've actually done everybody. Okay. We look at all the paths, and we now know that we can get from to 5 and 7 at a cost of 3, and we can get to any of the others. We've now written them all down. Okay. This kind of search is called a breadth-first search. Okay. Basically, it's spreading out from the initial point, kind of like going like all the points that all the vertices that initial one goes to, and then it goes to all the ones those go to, and it goes to all the ones. So it's spreading out like that. It's called a breadth-first search. Okay? It's actually very, very similar to level order in a tree. And remember, level order was this level, then this level, then this level. So you go like in this direction, right? You go the top level, everybody in that level, then this one, then like that. This is a very similar sort of algorithm. Except now it gets a little weird because things point back up, and it's, point back up to other places. Again, there's no like structure to this. It's the Wild West. Okay. Questions on that? Okay. Question is, though, how do you actually program this? Right? What we can do is we can keep a little table. All right, and that table holds the information about the search that we're doing, and we just update it every time we do something. Okay, and this is like the algorithm development process, right? What you do is you've got the vertices in the table, and then you've got whether they're known or not. And I put that in quotes because if something is known, it means we've handled it and we are done with it. And it would go from false to true. Okay, once you've taken care of it. The distance is how far away it is from the vertex. Notice we're going from 3. I've already put the distance of 0 in there. We actually we don't know 3. 3 is not known yet because we haven't dealt with its vertices that it goes to. Okay? So in this case, we're going to start with this table here. The one that we're starting at has a distance of 0, and everybody's not known yet, and everybody else is infinity distance away because we don't know how far away they are. Could you do this and have something that's still infinity away at the end? How would we do that?
It would be a dead beacon, or like something that you couldn't get to from 3.
Yeah, if you started at 6, everybody would be infinity, right? Because you can't get to anybody from infinity, right? If you go to Google Maps and say, I want to know how to drive to Hawaii, it used to be that they said, sorry, you can't get there from here. But now they say, go to San Diego or whatever and get on a jet ski or get on a boat or canoe or whatever. But you can. There are places, right? If you said, take me to the moon, they probably wouldn't be able to do that. Or they might say, drive to Florida and get on a rocket or something. Yeah, I don't know. Those Googlers.
Like if you're signed in as Elon Musk, it might give you directions.
Exactly. If you're right, you give you directions at that. Okay, so that's how we do. So let's just quickly run through this algorithm. How we would do this. It's exactly the same thing, and I'll go through it. Well, not quite yet. This is the actual code. You don't need to memorize this or look at it, but basically, it's just saying for every vertex, if it's already known, or if it's not already known rather, and you're at the current distance, then you need to take care of the ones that you're going, the vertices that come from it. Okay, and the problem with this algorithm is actually that if you get weird degenerate graphs like this, it can be n squared behavior, or I guess v squared in terms of the number of vertices. So this isn't the best algorithm in the world, but it does work. We'll do a slightly different one in a little bit. Okay, don't worry about the details of the code right now. You can look at them online. Okay, all right, let's walk through this one. So we start with the vertex 3 is 0, and then we're going to do 1 and we look at 1 and 6. And 1 and 6 now we make them 1, and it's just updating the table. It's like the bookkeeping part for this whole thing. And now that we've taken care of everything that v3 points to, it is now known. We are done with it. And if something's known, you don't ever need to go back to it. Whoops. OK. So then we do 2 and 4, right? Because we go to 1, and for 1, we go to 2 and 4. And then 2 and 4, we make 2. We just add 1 to it, right? And then we set 1 to be known. And then we do the same thing for 6, except 6 is actually, don't need to worry about 6 because there's no adjacent vertices. OK, so 6 becomes known. And then we go to this v2, because that's the next one. It's exactly what we did earlier, right? And v2 goes to, let's see, 2 goes to 5 and 4. So we're going to make 5 and 4. We're going to update 5 and 4, except 4 doesn't need to be updated because it's already 2. OK, in fact, it's just because it's less. We don't need to update it. OK, and then finally we go to, so we update v7, right? Let's see, that was from 4. Same thing. 3 was already less, so we're going to update that. And then finally we process v5 and v7. And there's nothing to do for this one because this is already less than the 4 that would be. And then 7, same thing here. 1 is already less than the 4 that it would be. OK, and then your table ends up, everybody is known, and you've got all the values here. So it's not a hard algorithm. It's just going through it a few times to get it. Yeah, Aaron?
When we did the level order, you said you gave us a way that we could use a queue to do it. Would that make sense for something like this? Because you could take v3 and you could stick it in the queue, and you could make more, like 1 and 6, and stick them in the queue.
Absolutely. This is exactly the same thing. Yeah, you do use a queue for this.
Oh.
Yep. It's like you wrote my next slide for me.
Okay, great.
All right? Yeah, it's exactly the same thing. You use a queue for the vertices that we've already seen, and you stick them in the queue, and then you stick the vertices that go with that one into the queue. And then if you handle them in a first in, first out basis, you end up going through this algorithm quickly. Yeah?
If you compute the shortest path for all of the vertices from one vertex, is there a way to take those values of the distances and then compute the shortest path from any of the other vertices, or do you have to do another breadth first search for each starting vertex?
That's a good question. I believe you have to do a whole other breadth first search. There may, in fact, that's probably a good question, and people have probably thought of that a lot as far as can you leverage the amount of work you've already done for part of the graph on another part of the graph, or to do a different question. Yeah, I'm not sure though. Good question. Yeah, very good question. Okay. All right. So that's so we can use this queue. In fact, I do write out the little queue code here. This, if you remember from the, let's see, it was the Q lab, right? I guess it was the level order lab, the one we had to use a queue. It's almost identical to this. Remember how while the queue is not empty, we in-queue something. While the queue is not empty, we dequeue it. And then for every vertex, we actually in-queue the vertexes. It's exactly the same. This is a breadth first search. It's like level order and so on. Okay, in the last lab, we'll do a graph lab where you'll do this kind of search. So you'll have to remember how to do these things. Okay. All right. Any questions on that? Yes?
Does this do better than order v squared?
Does this do better than order v squared? Yes. I believe this one does better than order v squared, although, yeah, it doesn't have to redo. It doesn't have to go from everybody to everybody else in this case, because you've already once something is known, you don't have to go back and do it again. So I think you're better than that. I didn't actually look up what the actual logarithmic behavior for this one is, or asymptotic behavior is, but I will look that up. So now this brings us to probably the most famous algorithm in computer science. Okay, this is called Dijkstra's algorithm, named after this guy named Edgar Dijkstra. I'm getting his name wrong now. And he is a famous computer scientist, started doing his work in the 1950s, came up with a ton of different algorithms and like computer science stuff. Still alive, I believe. Hope I'm not mixing up with somebody else. I believe he works at like University of Texas now, but he's actually from overseas. One of the very few people who has an IJK actually in his name, like right next to each other. Right? I don't know. And he came up with this algorithm to do the same idea of shortest paths, but now we're going to do the shortest paths on a weighted graph. Okay? This is the kind of thing that your Google Maps is going to do. Okay, this is the kind of thing because you're going to have to know different weights. What the weights are depends. Like they're going to be really clever about it. They're going to take into consideration what? What is Google going to take into consideration when they're trying to get you to point A to B? Yeah. Traffic. Speed limit.
Number of lanes?
Number of lanes. Yeah, I guess that's probably traffic in that sense. But yeah, well, it's kind of thing. Yeah, Nathan?
Traffic lights?
Traffic lights, sure, if they know that. And they know that because like they can monitor your Android phones and like pick out a lot of that stuff, right? What else? There's one other thing nobody said, which is surprising. Yeah, distance, right? They're going to, of course, know distance. So they're going to take all of those into account, and they're going to do a lot of these calculations, like in real time, trying to figure out where you're going. Like if you're doing it live traffic control or whatever, you're trying to find out where you're going. Sometimes Google will actually change your route midstream because it figures out, oh, there's an accident ahead or there's something else going on. Yeah, so they'll do it like that. Yeah.
Actually, never mind. I think it's probably.
Okay, so this algorithm is a little bit tricky. What we'll do is I'll briefly go over it now, okay, and then we'll revisit it first thing on Monday as well to kind of remind you. There will be questions about this algorithm on the final, so you'll have to figure it out. If this doesn't make sense, you'll have to figure it out eventually. Dijkstra's algorithm, somebody mentioned this earlier, is known as a greedy algorithm. Okay? What it does, it's greedy in that it says, right now, what's the best path for me to take? Wherever I am in the graph, from what I can tell about the rest of the graph from where I am, what's the best thing for me to do? I'm going to do that. That's what a greedy algorithm means. Okay? Greedy algorithms are cool because sometimes they do amazing things. Right? You can walk through like mazes and things using a greedy algorithm really fast if it happens to be a good algorithm. Sometimes, though, greedy algorithms don't work. Okay? Let me show you an example of a greedy algorithm. Back to change here. Anybody ever work retail? Got to count out change, right? It's kind of painful, right? And you kind of, depending on whether or not you like the person you're serving, like you'll count out like correct change in the minimum amount of coins, or you'll give them like lots of pennies and things if you're like being mean, right? But if you want to count change and you want the minimum amount of coins, okay, you can use a greedy algorithm. All right? What you do is you count the greatest coins first, and then you count the smaller coins. So first you count quarters, then dimes, then nickels until you get up to the amount that you're looking for. Right? Pretty simple. And you'll always end up with a minimum number of actual coins if you do that, as it turns out. Okay? 15 cents change. What do you 15 cents change? Dime, which is the biggest that goes into 15, right? You can't use a quarter. And then a nickel, 2 coins. Okay? That's a greedy algorithm. And it works great for coins that we have. What if I added a different coin? What if I added a 12-cent coin? Okay. What would we call a 12-cent coin? I don't know. I called it a 12er. I don't know what you call it. A does. I don't know. Right? If you wanted to make 15 cents change with a 12er, what you would do is you'd grab the 12er and then you'd say, okay, well, once I have 12, I can't use any nickels, so I have to go to pennies. And then 1 12 and 3 pennies gives me 4 total coins. But the greedy algorithm actually failed in this case because you can do it with 2 coins. You can still do it with a dime and a nickel. You can't, and that's only 2 coins. Okay? So you want to be careful when you're doing some of these greedy algorithms because sometimes they don't work. Turns out Dijkstra's algorithm is one that does work. Okay? But you just need to know that sometimes it won't always work. Okay? All right, here's how it goes. You also go in stages, just like you do with the other algorithm. Okay? You select a vertex, which has the smallest distance among all the ones that are not known yet. That's the part that's the greedy part. It says who's the smallest from who's unknown yet. I'm going to take that one and do it next. Okay? And then you now declare that that's now the shortest path from one location to the next. It may not be, but eventually the algorithm will catch up and figure out the right answer eventually. But this minimizes the number of different ways you have to go, or places you have to go. Okay? So at each stage, you decide whether it's a good idea to use a weight or a path and go with it. And then in the end, it works out just fine. Okay? Here's how we're going to do more of these tables. Okay? I'm only going to go through this once, and then I'm going to let you rest because this is a hard thing to do. And then I'm going to go through it again Monday. Whoops. Okay. The initial configuration for our table here. I've added another column called the previous one. This is the one we're going to come from last. What this will allow us to do is print out what the shortest path is. We didn't even talk about that in the last one. Like, how do you actually know what the shortest path is? You know that what the amount is, but now we want to actually find it. It would be kind of silly if Google said, OK, to go from here to New York City, it's going to take 4.5 hours. And that's all they told you. They didn't say go left, go right, go. They just said 4.5 hours, go. Good luck, right? But that, you gotta, you want to know where you came from. OK, but the same idea otherwise. Everybody starts out unknown. The one you're going to, in this case, we're going to go from vertex 1, in this case, to all the others. OK? You start at 0. That is a path of 0, a distance of 0. Everybody else is infinity because you don't know what they are yet. OK? All right. So what do? We start out and we go, look, 1 we now is known. OK? And the ones that the adjacent to 1 are 4 and 2. So you mark those by, you can't just add 1 now. What do you add? The weight of the one that of the path that you're going to. So the weight from 1, which is 0, to 2 is just 2, and the weight from 1 to 4 is 1. So you update the charts like this. Don't say that these are known yet, because they're not. We're just updating their distances. And what you also do is you say, hey, where did it come from? The one that we're just dealing with is vertex 1. OK? All right. So now the algorithm says, choose of the ones that are unknown, choose the one with the smallest distance. So which one are we going to check next? 4. Why? Because it's unknowns, right? The only ones that are unknown are these ones. Of those ones, what's the smallest distance? 4. We have to go to 4 next. And we go to 4 and repeat the process. Okay? 4 is nice. It's adjacent to a ton of different things, right? 4 is adjacent to 5 and 7 and 6 and 3, right? So you update all of those. Okay? From 4, you can get to, for 5, you are going to add 2 to whatever 4's path is, right? So let's see, that would be 3. And for, let's see, for 7, you're going to add 4. But guess what? Oh, actually, is this one? Did I do that right? Oh, yeah, it is. 4. 4 plus 1 is 5, duh. OK. And then for 6, you're going to add 8. And that would be 9. And then for 3, you're going to add 2 to the 1, so it's 3. OK, see how we did that? We just updated all those. And then we set 4 to be known, because it's now known. OK, what's the algorithm say? Pick the least of the ones that are unknown. So the unknown ones are these ones. The one that's the least are 3, 9, 5, and 3. If there's ties, you get to choose if there's ties. Oh, there's 2? Oh, we didn't do 2. I forgot. Sorry, we'll do 2 quickly. There we go. We do 2 next. 2 goes to 5, and it goes to 4. In both cases, right, the 5 is not going to get changed because it was already less than the amount that you would add. Because you would be adding 10 to 2, and you get 12. But look, 5 is already 3, so you don't even change it. OK? And for 4, same thing. It's already actually known, so you don't even need to deal with it. Right? So that's done. You don't need to do anything for 2. Then we choose the one that's of the remaining unknowns, what's the least. You've got 2 choices. Choose one, whichever one you want. Let's do the 3. OK? Mark 3 as known, and same thing. We're just repeating this. Mark 3 as known, and 3 goes to, where is it here? 3 goes to 1, which is 0, so we're not going to change that. And it goes to 6, and it would be, let's see, 3 plus 5 is 8, so that's less than what it was. So that's going to go to 8. I think it was 9 before. Yeah, OK, so it goes to 8. And that gets updated. And then 3, rinse and repeat, right? You're going to do, of the remaining ones, you're going to have to pick 5. You're going to do that one. OK? Mark 5 is known, and then nothing changes with 5 again, because the only thing it goes to is 7. 7 was already had a value of 5. You're not going to add 6 to 3. You're not going to make it 9, because it's less already. Question, Jean-Marie?
Yeah. So did you say that if it's known, we shouldn't change the distance?
If it's known, you don't need to. You know it's already going to be the least, as it turns out.
But like when we're doing before, because we chose the last.
Because you already chose the least amount from there, yeah. So yeah, that's the greedy part about it. Yep, absolutely. Yeah, good question. Yeah, it does take a little thinking. Oh, are you sure? And you don't. You actually don't have to ever change it again if it's already known. And that's the point of being known. So the only two left are 6 and 7. You would do 7 next, okay? And 7 goes to 6, but it's and in this case, it would be one more. So 5. So let's see, 6, 8. So it's going to be 6. So you're actually going to change that to 6. Okay, I believe. There we go. And then 7 is going to be 7 is going to be known. The only one left is 6, and you're not going to have to do anything with that because it actually doesn't go to anybody, and you're done. So that's Dijkstra's algorithm really, really fast. We will go over this again on Monday, and we'll go through some more examples. But you gotta kind of just remember those key issues. If you haven't dealt with it, if it's unknown, pick the smallest of the unknowns and go for the adjacent vertices to that. Yeah.
So in order to calculate, if I just pick 2 that I wanted to go from, like I wanted to go from V1 to V7, what I would do is I would run the greedy algorithm and have it stop when V7 became known and have it.
Yeah, sure. Yep, absolutely. Yeah. It's like, I mean, Google's not going to say, I'd take you, figure out how to get you to San Francisco if you're trying to go to New York City, right? It's going to stop when it gets when New York City becomes known, right? Which could happen. I mean, who knows? It could happen through San Francisco if some weird, wacky, like, super speed train came along, I mean, where there was something like that. Yeah, who knows? Yeah.
Is this NP time?
That's a big question. Is this NP time? I won't answer that right now. But just it is. You should look up whether it's not. Don't worry about what that question is. But is it based on it's n squared time really, right? Because you only need to go to the total, or I guess v squared in terms of doing it. I believe this one's v squared time. Yeah, it's not unknown, but it's I'm not 100% sure. You can look that up. Or I'll look it up and get back to you. Okay, so. By the way, we also know which the previous one to go to is. So if I want to get from 1 to 6, right, how do I print out what my route is? Well, I just go to 6, and I say I came from 7, and then 7 I came from 4, and then 4 I came from 1. And it's backwards, but that's the path to go from 1 to 6, right? You just go backwards, and it's just a pretty simple, recursive algorithm to do that. Okay. All right. Let's see. That's that for the thing. So questions on this? We are going to go over it again. Don't worry about if it made your brain spin a little bit. But that's your first real greedy algorithm, and it's, as I said, one of the most famous ones. Okay. All right. Any questions? I'm actually going to let you go a little early. Brain might be full anyway. All right, see you guys Monday.